In this video, we'll be looking to identify and label the properties of a variety of three-dimensional shapes. We'll look at how to draw accurate plans and elevations of 3D shapes, and then also create two-dimensional nets of these shapes. Before watching this video, I'd recommend watching the video on polygons, as many of the properties of those polygons are used in this video. Let's start by looking at some two-dimensional shapes. As we go through these, we want to note their names, the number of faces the shape has, that is to say the number of surfaces that it has. They may not necessarily be flat. The number of edges, which is where two faces meet, and the number of vertices it has, which are normally where three or more faces meet or come to a point. These are otherwise known as corners. This first shape that we have, you'll all recognise as a cone. It has two faces, the curved part at the top and then the circle that's around the bottom. It's got one edge where the curved upper part meets the circle, and it's also got one vertex or corner which is at the very top. The next shape is a cylinder. This has got three faces, a circle at the top, a circle at the bottom, and then a curved part that goes around the middle. We'll be looking at this further when we look at nets to see what type of shape that actually is. It's got two edges where the circles join that central curved section, and this shape doesn't have any vertices. This next shape here is called a sphere. Very simply, it's a ball. It has one face, no edges, and no vertices. Here we have a very common shape called a cuboid. It has six faces which are rectangles. Remember, squares are also rectangles. It's got 12 edges, 4 around the left, 4 around the right, and then 4 around the central section. It's got 8 vertices or corners, 4 on the left, 4 on the right. The shape could also be called a rectangular or square-faced prism, but we use it so often we give it its own name of cuboid. Other prisms, such as the next one, are described by their non-rectangular face, such as this, which we would call a hexagonal-faced prism. The hexagon will be repeated at the back or at the bottom of the prism. All other sides are rectangles formed by the parallel edges that run down from its vertices. It's got 8 faces, 1 on the top, 1 on the bottom, and 6 around the central part. It has 18 edges, 6 on the top, 6 on the bottom, and 6 around the outside, and it's got 12 vertices or corners, 6 on the top, 6 on the bottom. Now, if that was called a prism, and it's described by its front face, which in that case was a hexagon, this is another type of shape which is called a pyramid, and it's described by its base. In this case, it's a square base pyramid. It has 5 faces, 4 triangles, and the base, which is a square. It's got 8 edges, 4 around the bottom, and then 4 around the triangles going up. It's got 5 vertices, 1 in each of the corners and 1 at the top. Here we have another 3 shapes. This one looks very similar to the cuboid that we've just looked at. However, it's made up entirely of squares, and because of this, we call it a cube. Apart from the fact that the 6 faces are square, it has exactly the same properties as a cuboid. 6 faces, 12 edges, 8 vertices. Next, we have another prism. This time its face is a triangle. And again, it has rectangles at the sides, and that front triangle is repeated at the back. We have 5 faces, 1 at the front, 1 at the back, and 3 around the central section. It has 9 edges, 3 at the front, 3 at the back, and 3 around the central section, and 6 vertices or corners. Lastly, we have a triangular base pyramid. This has 4 faces, as it's made up of 4 triangles. Although they don't need to be equilateral triangles, they very often are. It has 6 edges, 3 around the base and 3 going up the sides. It has 4 vertices or corners, 3 around the base and 1 at the top. Those are some of the 3D shapes that we'll look at. As you can imagine, you could have many more faces to a prism or a pyramid, but remember to describe them as the front face for the prism and the base for a pyramid. Next, let's look at some two-dimensional representations of these shapes. And the first method we'll use is called plans or elevations. When we describe elevations, we are referring to perspectives or points of view. These perspectives gives you a two-dimensional view as they would be perpendicular to one of the faces. Very often the perspectives are labelled with arrows or names. The view from above is given a special name of a plan or a bird's eye view, and it can resemble the footprint of the shape. Here we'll see a three-dimensional shape. The front elevation would take the same measurements as the front of the shape, as it is made of centimetre cubes. This means if we draw the front elevation, we can draw it as 4 across, 4 up on the left, and 2 up on the right. It then goes in 2 on the right, up 2, and across a further 2 to the left to create the face of the shape as a two-dimensional representation. From this direction here would be called a side elevation, as it takes on the shape of a flat rectangle. I was advised shading one of the two faces represented here to show it has a different depth or distance from the point of view that the side elevation is taking. Notice how I've placed the front and the side elevations on the same level, so we can see that the heights are the same. Lastly, we have the plan, or the bird's eye view, and again, we have two different depths, and as I shaded the nearest one on the side elevation, I'll shade the nearest one on this one. Let's have a look how that can be used in an exam question. Here we have a diagram that shows a prism with a cross-section in the shape of a trapezium. All the measurements are in meters, so this would be quite a sizable object. We're asked to draw the front and the side elevation on the centimetre grid, and we're given the scale of 2 centimetres to 1 metre. The first thing I'm going to do is I'm going to convert each of the measurements I think I will need to draw this accurately on the grid. As each metre is to be scaled to 2 centimetres, these 2 metre measurements will become 4 centimetres. This 1 metre measurement will become 2 centimetres, and this 0.5 metres will become 1 centimetre. I'm not going to worry about the 2.5 metres, as I think I can get the accuracy with the other 3 horizontal or vertical sides. I'll start this drawing here and place small crosses at the corners of the two-dimensional shape that I'm going to be drawing. If I was doing this on paper, I'd be using a pencil, as it's easier to adjust for mistakes then. I'll join up the points for the front elevation and then complete the trapezium with the diagonal side, joining the other 2 lengths. I'll create the side elevation on the same level to the front elevation so I can use the height to ensure I don't make a mistake in the perspective. Again, I'm going to shade this front face to differentiate it from the sloping plane that doesn't really show up on the side elevation, but I can see it on the front elevation. Here, we're given the plan, front elevation and side elevation of a solid prism, which are drawn on a centimetre grid. They're asking us to draw a sketch of the solid prism and write on the dimensions. Now, I'm not very good at drawing, so I'm relieved to see that this asks for a sketch, which allows it to be less accurate than on the centimetre grid. It also asks for the dimensions to be added. So what I lack in accuracy on my sketch, I can make up for with my notation. As long as I can give it some semblance of the shape and then give it the correct units of measurement, I should be fine. I can see that it's 5 centimetres along the base from the front elevation and 4 centimetres up on the left-hand side. So I'll draw a line about this long and then a line going up that is slightly shorter than the base. I'm going to roughly draw the front elevation as seen on the centimetre grid. Then I'm going to draw a line at around 30 degrees from the horizontal to represent the 3 centimetres of the base of the side elevation from each of the corners. This will give it a 3-dimensional representation, and then I can join all of those up to create the back edge. Now I can put the measurements on, starting with the 4 centimetres on the left, 5 centimetres on the base, and 3 centimetres on the depth. These back edges are all 2 centimetres, with the exception of this top one that's 3 centimetres. So here we've completed the 3-dimensional sketch of the shape. Next, let's look at creating some nets of the 3D shapes, which is going to come in very useful when we go to calculate surface area in the next video. Here we've got a triangular prism that we saw right at the start. We need to describe the shape of the faces and the nets that this will match. The net is a 2-dimensional shape that's formed if we were to open up the sides and flatten them out to create a 2-dimensional compound shape. As it's a prism, we know that the sides will be rectangles and the front and the back will be triangles. So I think it's going to be net C, as we can see 2 triangles and 3 rectangles that make up the faces. Here I've got a cube. Remember that there are 6 faces to a cube and each of them are squares. So that means it's going to have to be net G. As we can see, each of these shapes that make up this net are squares. And if we were to fold this together, it'd come together to make a cube. It's important to check that none of the faces of the net will overlap when folding to create the 3D shape. Next, we have a triangular pyramid. As we know, this shape has 4 faces and they're all going to be triangles. We can recognise this is going to be net E. Now this net shows 4 equilateral triangles, and it could well be that this is accurate. However, they don't need to be equilateral to create the pyramid. Now we have a cone. If we were to unfold the faces of this shape, we'd see a circle on the bottom and then another shape that will look almost like a semicircle. We can see this is going to be net A. This part here is called a minor sector. We'll look at them in further detail in a future video on circles. Lastly, we have a cylinder. As we said at the start, a cylinder will have 3 faces. The top and the bottom are going to be circles, and this curved edge which will unfold to form a rectangle. So this must be net D. An interesting aspect of the net of a cylinder is that the length of the rectangle is going to be the same as the circumference of the circles. It always seems to be longer than it should, but it should be noted that it's going to be at least 3 times longer than the width or diameter of the circle. We'll look at that in more detail in the circles and the surface area video. So in this video, we've looked at identifying and labelling all the properties of the 3D shapes that we saw, with reference to their faces, edges and vertices. We then looked at how to draw accurate plans and elevations of shapes, and also how to recognise and create the nets of the 2D shapes, so that it makes up their faces. In the next video, we'll be using nets again, where we look to calculate the surface area of 3D shapes. I'll see you then.